Hello everybody, welcome back to Monte Carlo Methods. In today's video, we're going to talk about how to simulate from the normal distribution. A one-dimensional normal distribution will eventually get to higher dimensional normals. Now, as a one-dimensional continuous distribution, we have two techniques that we could use at this point. We have the inverse CDF method and the accept-reject algorithm. The inverse CDF method is not a great idea because we can't write down the CDF for the normal distribution in closed form, much less invert it. Now, you may be able to do some sort of numerical approximation for the inverse CDF of the normal distribution, but why bother introducing any sort of approximation when we can simulate from the distribution exactly? As for the accept reject algorithm, you'll recall we need to bound the normal PDF by something and be able to integrate and be able to draw from something. And there is an accept reject step where we go, nope, nope, nope. Okay, you finally accept something. Now, there's no reason to go through such a process, which could be inefficient when we have exact methods that work for the normal distribution. We're going to talk about one of these today. But yes, in theory, you could use the accept reject method. As a reminder, the continuous random variable x has a normal distribution with mean mu and parameters sigma squared. Now, these are both parameters. Mu is anywhere from minus infinity to infinity, and sigma squared needs to be strictly positive. If x has PDF 1 over the square root of 2 pi sigma squared, that's all under my square root, e to the negative 1 over 2 sigma squared times x minus mu quantity squared. And x here goes from minus infinity to infinity, and we usually write x, squiggly line, has the distribution, and then an n for normal, and then a mu, comma, sigma squared. Now, if you take the positive square root of the variance of sigma squared and call it sigma, that parameter is known as the standard deviation for the distribution. The mean parameter mu is a location parameter, and I'm going to graph this for you, but this is the standard or ubiquitous bell curve PDF, and it's centered at mu. So as you move mu, you move the bell curve along the real axis. And the variance, or almost equivalently in terms of measuring spread parameter, as that gets larger, the bell curve gets squished and more spread out. And as it gets smaller, the bell curve gets more extreme and spiky. Now, it's not hard to show using standard calculus techniques that one sigma or one standard deviation away from the mean mu is the place where the curve changes concavity. So you can see in this picture, it's concave down here and then becomes concave up over here as you pass one standard deviation away from the mean mu. So this is another way to see the effect of changing the standard deviation. If you put that really, if you make it really large, then you're like concave down for a long time and eventually concave up and you get something really flattened and squished down with much heavier tails. Okay, so most of you, if you're in this course, I'm sure you've heard of the normal distribution, and I'm sure you also know that if you define a new random variable, I'm going to call it z, and you define it to be x minus mu over sigma, that this has a normal distribution with mean 0 and variance 1, and this is known as the standard normal distribution. On the other hand, if you start with a random variable z that has this standard normal distribution, and you define a random variable x by taking a sigma times z plus a mu, then you get something that has a normal distribution with mean mu and variance sigma squared. If I were to show this, I would use what I call the G inverse approach. That is not common terminology, but something I teach in my mathematical statistics course that I'll link right up here. Actually, that specific video where I talk about how you could show these transformations. I did say at the beginning of this course, and I still mean it, that I want this course to be as self-contained as possible. Now, if you haven't had mathematical statistics or Markov chains or Markov processes, you could go through this Monte Carlo course, and what you'll have is recipes. You'll be able to simulate whatever you want to simulate in the end, but I'm not going to be able to prove to you why the methods I'm suggesting work. So it would really be helpful if you had mathematical statistics and Markov chains. And if you could only take one, I would take my course or someone else's course, but I'm going to link my course in mathematical statistics here or my course in Markov chains. And again, it doesn't have to be my course, but those are my links. So let's proceed. And if you believe these transformations, or if you've had mathematical statistics and you've convinced yourself otherwise, then we can see that it's possible for us to just simulate from the standard normal distribution. And if you want to simulate from a more general normal distribution, you can then take the results of your standard normal simulations and sort of rescale and relocate them using these relationships here. So our goal for this video is going to be to simulate a random variable that I'm going to call capital Z from the normal distribution with mean 0 and variance 1. Again, you might do that using the accept reject algorithm, but again, why would you bother taking a series of steps and waiting until you have an acceptance when you can just do this in one shot? Now, there are multiple ways to do this, and the method we're going to talk about in this video is known as the Box-Muller method. What you need to do is to simulate two uniforms. I'm going to call them U1 and U2, independent and identically distributed from the uniform 0, 1 distribution. So in practice, you're going to get these two values from your random number generator. I'm then going to define two random variables, a z1 and a z2. Now, z1 is going to be defined to be the square root of -2 times the natural log of u1 times cosine of 2 pi u2. And of course, u1 being between 0 and 1, the log of that is negative, so this is a positive value under the square root. Now, I claim that this is going to have a standard normal distribution, but you see that it took us two uniforms to get it. And while we're at it, we can get a second standard normal random variable or simulated value or random variate or realization of a standard normal by using the same uniforms. I'm going to define z2 to be the square root of -2, the natural log of u1 times the sine of 2 pi u2. I claim that z1 and z2 are independent and both having the standard normal distribution. Now, maybe you only wanted one, but we need two uniforms to get one. So why not get the second independent normal 0, 1 realization for free? I did this 100,000 times. I simulated or grabbed 200,000 uniform 0, 1s from my random number generator, and I computed Z1 and Z2. And here is a histogram of my Z1s with the standard normal PDF superimposed. So you can see it looks really, really nice. If you have not had mathematical statistics or something similar, I would recommend exiting this video now. You've got your method for simulating from the standard normal distribution. And if you wanted to turn them into normal random variables with other means and other variances, we talked a few slides ago about how to transform from a normal 0, 1 to a normal mu sigma squared. Now, honestly, if you needed to simulate normals, you would probably be doing that using a built-in function in whatever software you're using, because there's always a built-in function that will give you normal random variable realizations. And it's probably doing something like this Box-Muller transformation under the hood. But for the rest of the video, I'm going to prove that this transformation is doing what I claim it's doing. And this really isn't going to make any sense if you haven't had mathematical statistics. So yeah, you might want to tune out now if what you're interested in is the Box-Muller formula. But let's go a little further. So, towards the proof, I want to remind you in a one-dimensional setting. Now, the normal is a one-dimensional distribution, but you can see here that I'm taking two uniforms and producing two random variables, z1 and z2. So there is something bivariate going on here. So first, let's talk about transforming between the distribution of, say, a single uniform to a single random variable. Or more generally, suppose, and forget the normal distribution for the moment, Suppose I have a random variable x that is continuous with a PDF, probability density function, f sub x of x. And suppose I define a new random variable, capital Y, to be some function g with capital X plugged in. And I'm going to assume, for what we're talking about today, that g is invertible and differentiable. Now, you learn in a course in mathematical statistics that the probability density function for y, defined through this function of x, is the PDF for x with g inverse of y plugged in times the absolute value of the derivative with respect to y of g inverse of y. This is how you do most one-dimensional continuous transformations. Of course, this is not going to work if g is not invertible or differentiable, but we have other methods for finding the PDF of transformations in those cases. I'm just talking about this case here. So why did I bring this up? This is taking one random variable continuous to one other random variable. But in the Box-Muller method, I have two uniforms going to two z's, if you will. The reason I bring up this formula is just because it is what more people know when they've had some mathematical statistics. We're going to go a little deeper into a two-dimensional transformation, and it looks really similar to this, but in 2D. So I think it's helpful to see this formula and then look at how it changes when you move to two random variables to two random variable transformations. In this case, we would use something known as the Jacobian method. So I'm not going to derive either method. I keep wanting to point to my math stat information card, but I kind of think I can only do that once in a video. So there's probably nothing up here right now. But if you have capital X1, capital X2, two continuous random variables with a joint PDF that I'm going to call f sub capital X1, capital X2 of the arguments little x1 and little x2. And if you've defined two random variables, capital Y1 and capital Y2, by using a G1 of X1, X2 and a G2 of X1, X2, what you need to do is invert this system. So just to talk about it algebraically and forget the randomness, I'm going to write these lowercase little y1 and a g1 with little x1, little x2, similar for little y2. You need to solve this system of equations for little x1 and little x2 in terms of little y1 and little y2. I'm going to define little x1 to be like a g1 inverse of little y1, little y2. And I'm going to define little x2 to be a g2 inverse of little y1 and little y2. An important thing to note here is that g1 inverse is not the inverse of g1, and g2 inverse is not the inverse of g2. The system, these equations must be inverted simultaneously, as you'll see when we do it when proving the Box-Muller approach. So, this is not an inverse of just G1 alone and not for G2 alone. Something simultaneous is going on here. But once you solve for little x1 and you have it in terms of y1 and y2, I'm going to call that function. It's just a name, G1 inverse of y1, y2. Same thing for x2. Once you solve for it in terms of little y1 and little y2, I'm going to call that function of y1 and y2 G2 inverse of y1, y2. Now, in the one-dimensional transformation, I did have a derivative of g inverse of y, and in two dimensions, this gets bumped up to be a Jacobian, which is a determinant of a matrix of partial derivatives. In particular, I'm going to call the Jacobian capital J. It's going to be a determinant of the partial derivative of x1 with respect to y1 going across the top row, the partial derivative of x1 with respect to y2, and then the bottom row similar, but we are starting with little x2. If you've worked with Jacobians and you've used like the transpose of this matrix in here, that's also okay. My Jacobian is known actually as a backward Jacobian. And if you're used to it in the other way, it's known as a forward Jacobian. And the formula I'm going to give you for the joint PDF for Y1 and Y2 is going to differ by a little bit if you're used to using the other version of a Jacobian. But I'm going to use this one here. And again, this is a determinant. This is not my way of denoting a matrix. It's a determinant of the matrix of partial derivatives. Now, the joint PDF for Y1 and Y2 looks like this. If you recall from earlier in this video, when we had just a single x going through a function g and getting a single y, we had the PDF for y is the PDF for x with g inverse y plugged in times the absolute value of the derivative with respect to y of g inverse of y. And you can see the analog here. The joint PDF for y1 and y2 is the joint PDF for x1 and x2 with the two inverse functions plugged in. So this is what you get for x1 when you solve for it in terms of y1 and y2. This is what you get for x2. And then times the absolute value of the Jacobian. Now, the Jacobian is already a determinant. It's a determinant of a matrix of partial derivatives. This is standing in for our derivative of g inverse of y in the one-dimensional case. And that formula had an absolute value around that derivative. This one does as well. So these are second vertical lines, if you will. The Jacobian was defined as a determinant, and here these are absolute value lines. For us in the Box-Muller transformation, we're starting with a U1 and U2, so this would be a joint PDF for the two uniforms. And we're producing what we're calling Z1 and Z2, so the Y's are going to be Z's in our case. Here's a reminder of what we have. And so this is like Z1 is a function G1 of U1 and U2. Z2 is a function G2 of U1 and U2. Now, this is another place where you might want to exit the video. You now know how to show that the Z1 and Z2 from the Box-Muller transformation are independent standard normal random variables, because what's left in this video is the detail, and it's really hairy, and I don't know how much it illustrates if you really want to go through this. So this would be another good exit point for the video if you want the formula for the Box-Muller transformation and how you would prove it. But if you're still here, let's try to prove this. Now, it is convenient to automatically transform the support for any PDF, one-dimensional, two-dimensional, or otherwise, using indicators. If you've taken mathematical statistics with me, you'll know that I am a very big fan of indicator functions. These are ways to build into your PDF where it is non-zero. So I don't tend to write my PDFs as some function and then like a piecewise function and say it's zero otherwise. I tend to write them on one line with an indicator function that will zero it out in the right places. And for transformations, I think it's really convenient to use these indicator functions because you end up transforming the support automatically. Now, this is a stylistic choice, and I will talk about this at the end of the video. But right now, we're going to go into the hairy details of showing the Box-Muller transformation, and I'm going to transform the support of the distribution really informally. Okay, here's my Z1, here's my Z2. I might make all of these lowercase letters for the algebra I'm about to do. It really doesn't matter. But let's talk about the support or what we're going to expect, the kinds of values we're going to see for Z1 and Z2. Now, U1 being uniform 0, 1 is between 0 and 1. It's never going to equal 0 or 1 with any positive probability. So I'm going to say it's strictly between. And this means that the log is strictly between negative infinity and 0. So when you multiply by -2, you get something that is between 0 and infinity. The square root of that still between 0 and infinity. With cosine and sine always between -1 and 1, you're going to be flipping some of these values that are between 0 and infinity to be symmetric, but on the other side of 0. So we're going to get that Z1 and Z2 are going to come out between -infinity and infinity. And if you're concerned about whether or not the flipping is kind of a symmetric thing, I just real quick want to show you a graph of the cosine of the 2 pi u2 versus the sine of the 2 pi u2. So I simulated 100,000 values of u2, a uniform 0, 1. I computed cosine of 2 pi u2 and sine, and I plotted those points here. And what you're seeing is points going around the unit circle and appearing to hit everywhere around the unit circle. So it's not like we're just getting certain angles here where we're going to take our square root of negative 2 pi u1 and potentially flip it only in some regions. We do see that we're going all the way around the unit circle. So I don't know if that makes you feel any better about my informal support transformation. But back to the Box-Muller transformation, I'm going to say little z1 just for the algebra is some g1 of u1 and u2, and it's defined like this. Same for little z2. We need to solve for little u1 and little u2. So this one's, a little tricky, but note that z1 squared plus z2 squared gives us the this guy without the square root and a cosine squared plus a sine squared, and this term is 1. So we end up with just this. And if you solve this to this for u1, you see that u1 is e to the negative 1/2 times the quantity z1 squared plus z2 squared. So we have inverted for the first variable. And let's invert and try to solve for u2. Looking at these again, if I divide, now I can do this in either order, but it's a little cleaner if I look at z2 over z1. This stuff's going to cancel, and this sine over cosine is going to turn into a tangent. And now I can solve for u2 using the inverse tangent or arctangent and moving the 2 pi over. So here I have an expression for u2, and this is going to be the second function of the original variable. So this is going to be my g2 inverse of z1 and z2. Okay, so here's the recap. We need to compute the Jacobian, and so I need to compute the partial derivative of u1 with respect to z1. And for that, we get something that looks like this. With respect to z2, very similar. Looking at u2 with respect to z1. Now, this may require you to go back a little more into your memory, your distant memory of calculus, but we get negative 1 over 2 pi, and then z2 over z1 squared, and then 1 over the quantity of z2 over z1 squared plus 1. That's all in the denominator. We get something similar for the other derivative here. Now, before going on, I'm going to think of this as z2 squared over z1 squared. I'm going to multiply the top and bottom of this fraction by the z1 squared, get some cancellation so that this looks like this. It'll be a little cleaner. And the Jacobian is going to be this times this minus this times this. So we've got these expressions here. When we write this out, we get this. If you rewrite this, we get something like this, and we get cancellation, and it comes out pretty clean, or much cleaner than I would have expected in the end. Okay, so using the bivariate transformation, we are going to need the joint PDF for U1 and U2. Now, those were both IID. They were IID uniform 0, 1 random variables. The PDF is just 1. And if I'm not using indicators, the joint PDF is going to be 1 times 1 on the region where U1 and U2 are both between 0 and 1. And technically, I should say and 0 otherwise, and 0 when these little u's are not in this region. I'm being a little bit sloppy here by not writing this as a piecewise defined function, but I need more space on my slide. So we're ready to go. The joint PDF for Z1 and Z2 is the joint PDF for U1 and U2. I'm going to plug in the two inverted expressions. So what we got when we solved for U1 and what we got when we solved for U2, I'm going to multiply by the absolute value of the Jacobian. Now, there's nothing really going on here. When I plug this into this function, we still get 1. So the meat of the joint PDF we're computing here really all comes from the Jacobian. I have an absolute value. I'm going to take the absolute value, basically just drop this negative. E is always non-negative. And when combined with our informal transformation, that the little z1 and little z2 do live on minus infinity to infinity, we see that the joint PDF for z1 and z2 looks like the joint PDF for two independent standard normals, because this PDF does factor. And if you factor it, you will see 1 over the square root of 2 pi e to the negative 1/2 z1 squared. So that's one of the standard normals, and 1 over the square root of 2 pi e to the minus 1/2 z2 squared, the other standard normal PDF. So you can see independence, and that z1 and z2 are standard normal. Okay, so this would be another good place to cut out of the video if you're okay with that. I do want to talk about treating the support of the distribution a little more carefully using indicator functions. And yet, spoiler alert, it's going to go badly. It's going to go badly here because I had to use the inverse of tangent. And when you think about what the function tangent of x looks like, it's that kind of s thing, but it keeps repeating and it's really not invertible until we restrict ourselves to a certain region. And that could be sort of arbitrarily defined. And we invert it only on particular regions. So, doing this transformation a little more formally with the indicators is actually going to fall apart on me. And that's because tangent is not actually invertible. And it's a whole special case thing that you have to look at really carefully. I kind of wish I didn't bring up the indicators, but I did. So, let me just talk about that really quick to wrap up this video. If I let capital A be just a set of real numbers, I could define something that I'm going to call capital I sub A of x to be 1 if x is in A and 0 otherwise. This is known as an indicator function. There are many notations for indicator functions. But if u is uniform 0, 1, the PDF for u, I would call f sub u of little lowercase u, it would be 1 if u is between 0 and 1, and you can include these endpoints or not, and 0 otherwise. I can now write this on one line as 1 times an indicator, and this is going to make the function 0 out where it should. Okay, so that said, if I have u1 and u2, IID uniform 0, 1, the joint PDF is the product of the marginal PDFs because they're independent, and they have the same PDFs here because they're identically distributed. And using indicators, we get something that looks like this. Now, I love using indicators when I do the transformations because when you plug in those inverse functions, you automatically get the new indicators and you don't have to think about the supports of the new random variables separately. Again, it's going to fall apart in this example though, because tangent is not really invertible until we restrict it to certain regions. So it's really, really messy for this transformation. But the joint PDF for Z1 and Z2 is supposed to be the joint PDF for U1 and U2 with these things plugged in times the Jacobian. Now I'm going to plug this into this indicator and this into this indicator. It's really a mess. How do you deal with this? So this is a final answer for the joint PDF for Z1 and Z2, but it's not easy to work with. And it's not really in a nice form because this is a joint PDF for a Z1 and Z2. And it would be much nicer to say where Z1 and Z2 actually live. So to make these indicators be indicators for Z1 alone, not for this big mess, and Z2 alone over here. So what I would usually do in a less messy example is say that this indicator is 1 whenever this expression is between, in this case, 0 and 1, and then try to solve for what that means for Z1 and Z2. Now, in this case, this e to a negative value is always between 0 and 1. And again, I could include these endpoints. It doesn't matter for continuous random variables because if both of the z's are 0, then this e will be equal to 1, but neither of those things is actually going to happen. But this is always between 0 and 1. So I don't need any indicator. I don't need this restricting my PDF. This indicator is always going to turn on and be 1. It can be dropped. The other one, as I've said several times now, is a little messier. This indicator is 1 when this expression is between 0 and 1. And we want to figure out what that means for Z1 and Z2. So it means that the inverse tangent of Z2 over Z1 is between 0 and 2 pi. And if you look at inverse tangent, it looks like this. And it kind of appears that we need our Z1 over Z2 because I'm looking at inverse tangent of x. And the only place it is positive is when x is positive. So it kind of appears that we need this to be greater than 0 in order for this to happen. And here's where the problem actually occurs. And that's because you can invert tangent over different regions. Remember, again, how tangent looks, kind of those limp S's. And we want some region where we're going to get both the positive and negative parts of tangent. And we could take like the positive part and the negative part of another piece of tangent. And so we could make this work, but this has become way more messy than I really didn't want to go here. I could edit this out, but I think I'm going to leave it. Normally, putting indicators through transformations is a great idea, not so much here. So, yeah, what a letdown. But you have a method for simulating from the normal distribution. Again, you're probably using a built-in approach, but again, it's a Monte Carlo course. We want to know in here what's going on under the hood, and this will help us come up with our own algorithms for simulating from other distributions that are going to come up in your research or your job when it's not a nice known name distribution with a built-in algorithm. So we always want to know what's going on. In the next video, I actually will have a second method for simulating from the normal distribution just for interest. It's known as the polar Marsalia method, and it's kind of what we just did in polar coordinates. So it's a lot of fun. You might want to skip it to get on to the next new topic in this course, but if not, I will see you there.